IT-related technologies are seamlessly integrated into every nook and cranny of our daily lives in this era, and among them, we spend our days constantly accessing numerous websites and web apps. Surely the most common thing we do daily is information search. Although we live in an age where voice search using microphones and searching directly from images captured by cameras exist, text search still dominates. Its accessibility is unparalleled regardless of age or gender. When we sign up for a new membership somewhere, we primarily input text information. The same goes for logging in. SQL, a special command, allows us to store, manage, and search for such text information. Even when searching for videos or sounds, ultimately metadata is recorded in databases, which we then search through. SQL is so widely known nowadays that even non-database engineers or web developers often come across it in news articles. SQL, in essence, is a language for communicating with machines for data management. As mentioned earlier, the most common function is undoubtedly searching. Logging in is also part of searching. It's merely finding and trying to match IDs and passwords. In fact, when modifying member information, we also use search. We need to retrieve that person's information first to make any changes. The crucial point is that tasks like storing, deleting, and modifying data occur relatively infrequently. Not many people sign up for or withdraw from memberships dozens of times a day, nor do they change their home addresses or phone numbers dozens of times a day. Unfortunately, the dangerous technique used by hackers, SQL injection, demonstrates its exceptional power in the search function that we use hundreds or thousands of times a day. This applies not only to corporate websites or web apps, but also to personal blogs or private websites. When we delve deeper into this indispensable aspect of our lives, the search, we find that it's powered by a command called select. When dealing with a large table containing information of tens of thousands or even millions of individuals, roughly this kind of command is used. Let's take a look, excluding complex conditions or table joins. The key point I want to convey is that SQL statements like these are much more prone to distortion than one might think. SQL injection, in other words, involves destroying or altering the syntax of SQL to create a different form of SQL. To do this, hackers need a way to somehow manipulate this statement structure. They find places to input something and illegally insert their desired SQL statements there. Of course, if they just insert another SQL statement, it will combine with the original one, resulting in a strange SQL statement that will likely throw an error and not work. But what if they invalidate the original statement and insert their own? For instance, SQL has a way of adding comments using hash marks or semicolons, just like in programming languages. If they use this before the part of the SQL statement specifying the search criteria, everything after it will be treated as a comment, rendering it completely invalid. It's like it never existed in the first place. That's the gist of it. The key point I want to convey is that SQL statements like these are much more prone to distortion than one might think. SQL injection, in other words, involves destroying or altering the syntax of SQL to create a different form of SQL. To do this, hackers need a way to somehow manipulate this statement structure. They find places to input something and illegally insert their desired SQL statements there. If there are no conditions, it'll fetch everything, right? Doing so would generate massive network traffic due to fetching large amounts of data. Now, folks, imagine if a malicious hacker could freely insert something into the position where the hashmark goes. It could lead to even more disastrous consequences. In reality, what users input would typically be the name or number of the item they want to search for. So, the input position would be precisely where 8080 is. However, putting a hashmark there would have no effect. But if they were to input 8080 there and then follow it with new conditional statements like AND or OR, the situation would change drastically. That's the gist of it. This is about checking if the condition after AND is true, a technique often used to sneakily figure out things letter by letter. The effect of this statement is that if both conditions are true, the name, address, and phone number will be outputted. Hackers can deduce if their injected statement is true by observing this output. In other words, for instance, this method could be used to find out if a person's name exists. Using a different approach, it could also be used to figure out the names of the databases or tables currently in use, letter by letter. That's the gist of it. Doing this, the database function would reveal the name of the database the current web page is using, and the hacker would use the substring function to extract the first letter of that name and check if it's D. If the query results in outputting the name, address, and phone number, then the first letter of the database's name must be D, since both conditions were true. If nothing is outputted, it means it's a different letter. By adding a hash mark at the end, it nullifies any other conditions that might come after. For instance, there could be additional conditions like matching an ID number with a specific date. By querying letter by letter in this manner, eventually, all the letters of the database name can be extracted. Of course, it might take considerable time, especially considering numbers or capital letters could be involved. That's why in practice, rather than manually querying like this, automated programs are used which can quickly retrieve the information. That's what the famous tool SQLMap does. Let's take a look at how it's actually used.
Let's attack the search page with SQLMap. Select will be used on the search page. It is easy to be exposed to attacks that collect information. The URL of the target, data to be transmitted, and information that the hacker wants to find out. I found out what database is used on the search page. Shall we find out what tables exist in the item box database? Apparently, there's a login table. Lucky. Then what we have to do next is obvious. Check what the columns in the login table are like. We don't know what table login T is yet, so if we find out the names of the columns, we'll be more certain, right? Shall we take out the data stored in the ID column and the pass column? Let's literally do dump. The data stored in the pass column is encrypted. Thankfully, SQLMap can crack encrypted passwords. Let's try decrypting the password. However, it doesn't work very well compared to professional password decryption tools. I stopped decrypting. It took too long. In fact, decryption takes a long time. I think we should get help from a more professional decryption tool. For example, a tool like Hashcat.
If you were to directly create SQL queries instead of using SQLMap, the approach would likely be something like this. If you look closely, there's another select statement being used, but this time it's querying the information schema, which is a metadata database containing schema information for databases. The aim is to find out the name of a specific table by retrieving the tables from the item box database and checking if the first letter of the name of the first table starts with U. The basic principle is similar to finding out the names of databases. By doing this, you can figure out the names of the tables within a specific database. Expanding further, since metadata databases also contain column information for specific tables, you can retrieve that as well, and ultimately even pull the data contained in those columns. Of course, it would require generating a huge number of queries to explore thoroughly, but in reality, SQLMap takes care of this for you. Now, let's delve into the technique using OR. If you pay close attention, another select statement is being used here, but this time it's querying the information source schema, which is a metadata database containing schema information for databases. The aim is to find out the name of a specific table by retrieving the tables from the item box database and checking if the first letter of the name of the first table starts with U. The basic principle is similar to finding out the names of databases. By doing this, you can figure out the names of the tables within a specific database. Expanding further, since metadata databases also contain column information for specific tables, you can retrieve that as well, and ultimately even pull the data contained in those columns. Of course, it would require generating a huge number of queries to explore thoroughly, but in reality, SQLMap takes care of this for you. Now, let's delve into the technique using OR. This disregards the existing conditions and searches based on the newly injected condition. The point is to deliberately make the previous condition incorrect so that the subsequent one executes. Without regard to the unique ID, it retrieves the name, address, and phone number of the person named Werewolf. Essentially, it exploits the original statement's searching capability to insert the desired condition and find out the results. This technique can be used to retrieve information about specific individuals as well as details about databases or tables. Another interesting technique involves using functions like sleep in SQL to introduce a delay until the search result is obtained. By utilizing this with the OR method, if the preceding condition is true, the search result will be immediately visible, but if it's false, the subsequent condition will be triggered, invoking the sleep function, resulting in a delay before the search result is displayed. This technique is particularly effective when a search command only yields simple output indicating whether something was found or not. While you can't see the detailed search results, you can determine whether your injected query was successful based on the time difference. To summarize everything so far, the ultimate goal is simply to ascertain whether the illegally inserted query was successful or not. SQLMap employs all these techniques to collect results. And collectively, these techniques fall under the umbrella term blind injection in web security. Protecting against such peculiar hacking attacks is quite challenging with mere filtering. As you can see, the variety of statements that can be used in SQL injection attacks is quite diverse. It's almost impossible for anyone, even SQL experts, to anticipate all of them. And even for experts, it's not easy to do with blacklisting. While it's possible to catch essential elements like hashes or double dashes, there's still no guarantee of complete safety. XSS attacks face similar challenges because of the ever-evolving array of expression methods. Truly bizarre techniques abound. Moreover, if the filtering were somehow to change, or if another method with the same function emerged, there would be no solution. Ultimately, an absolute defense mechanism became necessary, and the result is the creation of prepared statement, an extremely powerful technique that locks down the structure of safe SQL statements. From a developer's perspective, this technique is essential because it allows for the reuse of the approximate structure of SQL statements, but from a security standpoint, it serves as the ultimate shield. This is naturally employed by most modern frameworks by default, and the same effect can be achieved using ORM. From a developer's perspective, ORM is about not worrying about the structure of SQL and simply inserting the necessary data, so the principle is essentially the same. It's like being told to just do the interior design in a completed building. No matter how fancy the interior, changing the structure of the building is prohibited. In reality, it's roughly like this. This sentence gets stored in a variable. The part marked with percents is called a placeholder, and later on, the user's input data is inserted there. It's called binding. In languages like PHP or Java, you can see that only the appearance of these placeholders varies. And when it comes to binding, you just need to specify whether the data is a number or a string. So, in the code, you'll typically see functions like prepare that store the SQL statement, followed by functions like bind that assemble the data. Then, you'll see functions like exec that send the completed SQL statement to the server. If, during the binding process, the SQL injected by a hacker messes up the structure of the statement, it'll be caught and handled as an error. It's akin to doing interior design on a house and accidentally knocking down its pillars. Common techniques hackers use in SQL injection, like comment characters or cutting off statements with single quotes, will inevitably disrupt or destroy the original sentence structure, leaving no way to bypass the security measures. The point is, without altering or destroying the sentence structure, SQL injection can't accomplish anything. Now let's marvel at the power of this super strong defense mechanism. We're shifting the code structure from the old sequential style to an object-oriented approach. To employ the prepared statement technique, we need to code in an object-oriented structure. We'll transform the existing SQL statements into the new prepared statement format, leaving placeholders for the variable data parts in the SQL statement structure. We need to perform binding to fill in the empty parts of the prepared statement. Then, executing the prepared statement will do the job. Here's a sample from the PHP official website. When binding, we need to specify the data types of the data to be inserted into the SQL holes. There are various types for these data, roughly speaking. Since our search term is a string, we should use S. The completed code looks like this. Essentially, it's a scenario where we write the statement, bind it, and then execute it. This is where we insert data into the empty spots of the statement, represented by question marks, which we call placeholders. Let's switch to using a page with security measures applied. This is another coding structure using the prepared statement technique. The functionality is exactly the same, just with a slightly different code structure. Additional code has been added to display the search results on the screen. The search results will be displayed like this. Let's try attacking with SQLMap tool. If the defense measures are properly applied, even if we scan, we shouldn't be able to find any results. Roughly speaking, the result indicates that scanning is impossible. In other words, the database doesn't respond. It's because inserting manipulated statements won't change the structure of the statement. This is risking detection by scanning and proceeding with a powerful attack. Let's give it a try. We've applied the super strong option and tried again. But the result remains the same. The attack is completely ineffective. Finally, we've cranked up the scanning intensity to the maximum. Still, it's no use. Prepared statement indeed proves to be the ultimate defense mechanism. As you can see, this technology perfectly showcases how it's the ultimate nemesis of SQL injection. That's why emphasizing the use of prepared statements provided by frameworks or programming languages isn't just recommended, it's absolutely necessary. In fact, this technique is akin to using whitelisting for filtering in XSS attacks, making it the best approach.